Okay, today we will be looking at Chapter 5, continuing with our discussion on probability distributions. Specifically, we're going to be looking at a type of discrete probability distribution called binomial probability distributions. Before we get started with that, I do have some warm-up problems that I want us to go through. These are taken from my stat lab. In case you're having any problems with them, I just want to take a few minutes to go through these. So I'm going to give you a chance to pull it up and pause it and work with it and then check your answers on the next slide. Okay, on this one, you've got a table that's given. You want to find the probability, first of all, for getting exactly 4 sleepwalkers among 5 adults. So that's just literally going to be this answer here for 4. Find the probability of getting 4 or more. You're going to add 4 and 5 together, the probabilities for those, and get your answer for that. Which probability is more relevant? We discussed last video about how we're not so much concerned about what happens at one particular value as we are at like 4 or more or 1 or less, that type of thing. Is 4 a significantly high number of sleepwalkers among 5 adults? If you look at that, it would be considered significantly high because for comparison purposes, we want to consider the probability, and generally if it's less than 0.05, we consider that to be significant. Okay, here's another one for you to try. Okay, so here we have this table. So the table describes 10 births from 10 different sets of parents, and X represents the number of girls among the 10 children. So we want to find the range of values that are not considered to be significant. So in order to do that, we're going to need to find the mean plus or minus 2 standard deviations. So we need to know what the mean and the standard deviation are. So this is the process that we went through last time where we multiplied x times p of x and added them all up, and that gave us the mean. So I didn't fill in all those values, but this would be the mean that you should have gotten. And then for the standard deviation, we first have to find the variance. We find the variance by doing x squared times p of x and adding all of that together, which gives me this value. And then I'm going to take this value and subtract the mean squared from it, and that gives me this number here. That's my variance, and this is calling for standard deviation. So I'm going to take the square root of the unrounded value here. That's going to give me the standard deviation that I'm going to use. From there, I'm going to do my mean plus or minus 2 standard deviations. So when I do the plus side, I get 8.5, and when I do the minus, I get 1.7. So anything from 1.7 to 8.5, we would consider to not be significant. Anything outside of that would be significant. So in part B, it says based on the results, is 1 girl among 10 births a significantly low number of girls? So because it's outside of this interval from 1.7 to 8.5, it would be considered a significantly low number of girls. Okay, here's an insurance problem, and it's very similar to the one that we worked in the video, but I wanted to go back through it just because my stat lab asked some of these questions in a little bit different way. I just want you to be clear on what you would need to do there. Okay, so hopefully you've completed it and can check your work. The first thing we need to do is kind of identify our values. The probability that the person lives is given here. The premium charge for the life insurance is here. The payout for the policy is 100,000. And so from there, we're kind of ready to get this set up. If you remember, we make a column of X for our random variable, and that's the net gain or loss in each situation. So our two scenarios are that the man lives or that he dies. If he lives, he's going to lose his premium charge, and the probability that he lives is this 0.9992 that's given to us there. The other scenario is that he dies. If he dies, his family will collect the 100,000, but he'll have paid out the $167. So 100,000 minus 167 gives us this value. The probability that he dies is 1 minus the probability that he lives. So 1 minus this number gives me this number. And then from there, once I have this table completed, the expected value is simply the mean. So we're going to do x times p of x and then add those up. And that's going to be my expected value or my mean. So as far as answering the questions, the value corresponding to surviving the year, that's going to be this $167 that he's going to lose. The value corresponding to not surviving the year, that's going to be this value in case if he were to die that he receives. So if the 27-year-old male purchases the policy, what's his expected value? That's this value that we get here. And then can the insurance company expect to profit from many such policies? If so, why and how much? So basically, on average, they're going to profit about $87 per insurance policy that they write. Okay, so that takes us to today where we're going to look at section 5.2 on binomial probability distributions. Okay, like we said, the focus of this section is the binomial probability distributions and the way to find these different probabilities. We're going to use our calculator, and we are going to look at StatCrunch. We are not going to be finding binomial probabilities using tables. That is a method for doing that, as is formulas, but they're both very outdated, so we're going to be using calculators and computers and not tables and formulas. Okay. All right, so a binomial probability distribution has 4 requirements, and you need to know what these 4 requirements are. This is something you will be tested on as for the test coming up. Okay, so first of all, the procedure has a fixed number of trials. That's just your n. Your n shouldn't be changing, so you should have a definite number of trials that you're looking at for each probability distribution. The trials must be independent or at least be able to be treated as independent. So in other words, if we could use that 5% rule for cumbersome calculations, then that would be sufficient here. So they either need to be independent or be able to be treated as independent. And so a lot of times that's going to be the case, because if you're talking about like 10 people out of all adults, then you're definitely under 5% and would be fine with treating it as independent. So usually that's not a big deal. 3 and 4 are kind of the places that actually 2 and 3, sorry, are the places that we need to be most careful in checking to make sure that it does fulfill the requirements. 3 here is that each trial must have all outcomes satisfied into exactly 2 categories, and we're going to refer to those categories as success and failure. These are simply mathematical terms, so I don't want to imply any kind of positive or negative connotation to success and failure. Because in some ways I think they do kind of imply that, and it's not intended. For instance, in a particular problem, success might be defined as female and failure might be defined as male, whereas in another problem it could be the reverse of that. It really just depends on, success is kind of the characteristic you're looking for. Failure would be the complement to that. So, so the main thing is that you have the 2 categories, and we'll call one quote success and the other one failure, understanding that we're not implying any kind of connotation there. The probability of success remains the same in all trials. If you've checked off that it's independent, then your probability should not be changing, because if you remember, the only time our probabilities really change is when we have a dependent situation. Okay, and like I mentioned, you can implement this 5% guide for cumbersome calculations. If you're working without replacement, but the sample size is no more than 5% of the size of the population, then you are able to treat it as independent, even though it's actually a dependent situation. Okay, so I have a few for us to talk about and go through to determine if they're binomial. So the first one would be surveying 100 people to determine if they like a particular brand of soap. So their response here would be either yes or no. So they're going to have the 2 outcomes that we talked about, the success and failure. And as far as the 100 people, 100 out of all people, then definitely we would be able to treat that as independent, whether it was or was not. Tossing a coin 100 times to see whether heads or tails occurs. Well, here's our 2 categories, heads and tails. So again, that one would be binomial. Drawing a card from a deck and getting a heart. So a heart, if we look at this, we could get a heart, we could get a jack, we could get a spade or a club. Okay, so those are the 4 different suits that you can have with cards. And so because there's more than 2 different outcomes, then we would not consider that to be binomial. I will say this, if you look at it as hearts and those that are not hearts, then you can take a situation like this and make it binomial. So this would be kind of your success and this would be your failure of that. So it really depends on the context of the problem sometimes as to whether it's binomial or not, and how you interpret it. Okay, asking 100 people if they smoke, that's a yes/no question, so it would definitely be binomial. Asking 1,000 people to see whether they are admitted to White Oak College, again, it's yes/no, so it would be a binomial. Surveying 300 prisoners to see how many different crimes they were convicted of, because this could have more than 2 different answers, then it would not be binomial. Surveying 300 prisoners to see whether this is their first offense, then that would be binomial because it either is or is not their first offense. Drawing a card from a deck of cards and getting a black card, this would be binomial because we would have black cards, and for those of you familiar with cards, the others are red. So those are our 2 categories there. Okay, selecting 10 senators from the U.S. Senate to see whether they support the president. Okay, looking at this, at first, this does look like it would be binomial because you're checking to see whether they support the president, so it is a yes or no question. But the problem is we're taking 10 senators from the U.S. Senate. Okay, so here what we have is we have a small population. So for those of you familiar with the U.S. Senate, it's got 100 members. So we're taking 10 out of 100. Okay, so that's going to be about 10%, which is not less than the 5% that we need to have to be able to treat it as independent. And since we're assuming we're not going to be selecting the same senators twice here, this would not be able to be considered binomial. Okay, before we can get started doing calculations involving binomial probability distributions, there's a few things that we need to define here. We talked about success and failure being our 2 categories. So the probability of success is actually going to be denoted with this lowercase p, and the probability of failure is going to be the lowercase q. So we find q, since q is the complement to p, by doing 1 minus p. So anytime you're given p, you should always be able to find q. For instance, if p is 0.2, then q is going to be 1 minus that, so it's going to be 0.8. So they come as a complement pair, p and q. N is your fixed number of trials, and X is a specific number of successes in N trials. X is going to have to be a whole number, and it's going to be between 0 and N. So X is never going to be larger than your N. Okay, and we talked about the fact that success is kind of arbitrary and it's not intended to represent anything necessarily good or bad. One thing you want to be sure that you're consistent with and understand that they refer to the X and the P have to be consistent and they're referring to the same category. So it's important to define what success is so that you can carry that throughout the problem. Okay, so here's an example that I want to go through. When an adult is randomly selected with replacement, there is a 0.85 probability that this person knows what Twitter is based on results from a Pew Research Center survey. Suppose that we want to find the probability that exactly 3 of the 5 randomly selected adults know what Twitter is. So the first thing we want to do is answer the question, does the procedure result in a binomial distribution? So I'm going to go back for just a minute to our list of terms that we need, or list of requirements that we need to have. And the first, we need to have our fixed number of trials. So if we go back to this, okay, looking at this, we do have a fixed number of trials. Our fixed number of trials is going to be this 5. So we're going to select 5 for our fixed number of trials. I'm not going to flip back again, but the second one said that it had to be independent. and that the trials had to be independent. So we're taking care of that here with the with replacement. Even if it didn't tell us that, we would be okay though, because we're going to pick 5 people, and that's out of all adults. So 5 out of all adults is definitely a sample size smaller than 5% of the population, and therefore we're able to treat it as independent. The third, we need to have 2 categories. So here are 2 categories. We're going to let P be defined as those that know what Twitter is, and the probability of that is 0.85. So Q is therefore going to be those that don't know what Twitter is, and its probability is going to be 1 minus 0.85 or 0.15. Okay, and then the last is that our probabilities stay the same. Our probability is not going to be changing. We don't really have to worry about that because it's with replacement. So we kind of went through all the different all the different requirements to make sure that the procedure is a binomial distribution. Okay, if it is a binomial distribution, we want to identify these values here. So N, we said, is our trials, number of trials. So we're going to be selecting 5. X is going to be our number of successes that we're looking to find here. So we want exactly 3. We already defined our P to be 0.85, and our Q is going to be 0.15. Okay, and so this is just, if you want to see it written out, this is kind of what we talked about for verifying that the 4 different requirements. Okay, so I want to look at this binomial probability formula for just a minute. First of all, on MyStatLab, oftentimes they will try to show you how to do the problem by using these probability formulas. All it's going to do is confuse you if you're looking at that, because that's not how we're going to be doing it. We're going to be doing it with the calculator. I do want to just kind of show you the formula for one example here so that you understand how beneficial the calculator is. You can see here that P of X is n factorial. For those of you not familiar with n factorial, if I had like 3 factorial, that's going to be 3 times 2 times 1, and so forth with that. So we've got our n and our x. We've got another x factorial here. Then we've got p to the x and q to the n minus x. So a lot going on in this formula. Okay, so on this one, if we work with the values that we just identified here, what we're going to have is when we go to plug these formulas, these numbers into the formula, we had P of X is n factorial over n minus x factorial times x factorial times P to the x times q to the n minus x. So when I go and plug this in, my sample size was 5, so I've got this 5 factorial, and then I've got 5 minus the 3 was the n. 3 factorial goes here, my p, my x, my q, and my n minus x. So when I simplify this, I have, just put this in your calculator, each of these, and get these values here. If I'm going to write this out, 5 factorial will be 5 times 4 times 3 times 2 times 1. I'll divide that by 2 times 1, and then 3 times 2 times 1. So these are actually all going to cancel off, and the 2 will divide into 4. And so all that's going to equal 10, and that's where this 10 is coming from. So I'll multiply all of this out, and we get this answer. Okay, that's the probability that x equals 3. A lot of times we're going to want to know what the probability that x is greater than or equal to 3, which means you might have to add the probability of 3 plus the probability of 4 plus the probability of 5 together. If you were doing this by hand, you'd have to do a probability formula for each one of those. Thankfully, the calculator does that for us. So if you don't have your calculator out, go ahead and get that out so that you can follow along as we go through this. Okay, there's 2 functions on your calculator that I want you to be familiar with. One is the binomial PDF and one is the binomial CDF. So when you enter these in your calculator, it's going to come up either, if you have a newer calculator, it's going to come up with prompts that look like this. So for the trials, you're going to enter whatever the n is. So if n is 5, then you're going to put 5 here. P is obvious. I mean, you've already defined P and X. And then press enter, and it's going to give you your answer once you've entered all that in. So if you don't have prompts that come up like this, then the way that you're going to have to enter it is you're going to have to put N and then P and then X as far as the order goes, and put those in parentheses with a comma in between there. So as far as where we get this binomial PDF and CDF, if you go to your distribution menu, which is second and vars, so if you'll press the second and vars menu, it's going to bring you to the distribution menu, and go down to letter A for the binomial PDF, and go down to letter B for the CDF. Okay, use the PDF for the equals case. So anytime you're looking for a case where it's just equal to a particular number, you're going to use that case. And then anytime you're using any kind of inequality, so whether it's less than, greater than or equal to, less than or equal to, all of those you're going to use the CDF, because what the C stands for is cumulative. Okay, so if this is the cumulative total, then then it's going to add all of it up for us. And we'll get into the details of all this a little bit later. I just want you to be oriented to it. Okay, some people like formulas to do this by, others don't care so much. I don't personally use them, so I'm going to explain it both ways and you can decide. So if we have the less than or equal to case, then what you're going to do with that is you're going to use just the straight binomial CDF. So we said the PDF is for the equals case. The straight CDF case is going to be for the less thans and less than or equal to's. Okay, so if it's just less than or equal to, then you're going to do NPX, and you're not going to have to do any adjustments on it, because if we look at something that looks like this. Okay, remember we're talking about discrete probability distributions. So we would be looking at a chart possibly like this. So if we wanted X is less than or equal to 3, okay, what the CDF is going to do is if I tell it to go less than or equal to 3, then it's going to go and it's going to add all 3 of these up. So it's going to add the probability for 0, for 1, for 2, and for 3. It's going to add all those together and give me a total for them. So instead of you having to do a formula here, one here, one here, and one here, it's going to do all those and add them all together for you all at one time. Okay. The problem is that we only have the CDF, and we've got to still do all the other cases using that. So we've got to adapt it in a little bit different way here. So if I'm going to do just strictly the less than case, okay, I'm going to change colors here so we can kind of see. Okay, so let's say that we want to do X is less than 3. Okay, so X is less than 3, because this is discrete, there's nothing between 0 and 1, and there's nothing between 1 and 2, and nothing between 2 and 3. There's no decimals in here. So if I want X is less than 3, I've actually got to stop here at 2. Okay, so I don't go any further than 2. So when I go to put this in my calculator, what I'm actually going to do is I'm going to do the binomial CDF, whatever my N and my P are for that particular problem. And if this is my X, I'm going to take 1 from that, and I'm actually going to stop at 2. So I'm going to stop 1 short of where I need to be if it's a less than problem, because if I go all the way up to 3, I've gone too far. Okay, over here with the greater thans are a little bit tricky. I'm going to just kind of recopy this so I can talk about it. There's nothing special about how far I'm going here. It just depends on the problem. So on this one, anytime you have greater than or equal to, we're going to have to work with the complements to do this. So let's say we're going to do X is greater than or equal to 5. So if I want x is greater than or equal to 5, that's going to be 5, 6, 7, 8, 9. It's going to be all of these. So I want to find all these probabilities and add them all together. Okay, so I want the calculator to do that for me so that I don't have to do a binomial formula for each one of them and add them together manually. Okay, so the way that I'm going to do that is I'm actually going to have the calculator find this part here, and then I'm going to do 1 minus that to get this part here. So I'm going to do 1 minus the binomial CDF of whatever my N and P are for that particular problem. And if this is 5, then I want to stop one less than that. I want to stop at 4. So if I'm starting here at 5, then I need to stop the complement to it at 4. So this is actually referring to the complement to what we want. So this is what we want down here, and this is its complement up here. Another way to remember this is if 5 is included here, it's not included here when you're talking about these complements. Okay, on this one, if I'm looking at something like x is greater than 5, again, I'm going to change my pen color so we can see a little bit better what I'm talking about. Okay. So greater than 5, because we're talking about discrete and there's nothing between 5 and 6, I'm going to start it at 6 and go all the way to 10. So that means my complement this time actually goes all the way down and picks up 5. So when I do this, it's going to be the binomial CDF of whatever my N and P are for the problem, and then my X is going to be all the way up to 5. And you can remember again, if the 5 is included here, which it's not, then it's got to be, if it's not included here, it's got to be included here. Okay. So it can't be included in both places. I know at this point, this is a little bit abstract, but I think as you see us go through some problems with it, you'll understand how to set it up. Okay, so on this particular problem here, we're going back to the same Twitter problem that we worked with before. So if you remember, our N was 5, our P was 0.85, our Q was 0.15. So here we want to find the probability of selecting 3 or fewer adults who know what Twitter is. So 3 or fewer, we're going to write that as x is less than or equal to 3. So it's important that you get your correct inequality here. So we want x is less than or equal to 3. So I'm going to kind of draw this out over here because when we're talking about the Twitter example, either none of the 5, 1, 2, 3, 4, or all 5 know what Twitter is. Okay. So if I want the probability that 3 or fewer, that's going to be 0, 1, 2, and 3 all added together. And so I'm going to get my calculator to do that for me by doing the binomial CDF. My N is 5, my P is 0.85, and my X is 3. And again, your calculator may prompt you for, this may say the trials, this may say the P, and this may say something like X number of successes. Okay, so when you put that in your calculator, you're going to get 0.165 because we do want to round these to 3 significant digits. On the next one, the probability of selecting less than 2 adults. So that's going to be less than 2 would be like this. So I'm going to do the binomial CDF again, N, P, and then this time if I want less than 2 would be 0 and 1. So I need to tell it to stop adding. I don't want it to include 2 because I need it to be less than 2, so it needs to stop here at 1. So my stopping place is going to be 1. So this is telling it to add 0 and 1 and stop at 1. So whatever this value is where it's going to stop adding. So if I put that in my calculator, and again, you want to go to your distribution menu for that. And so we get 0.00223. Okay, moving on, exactly 4. Exactly indicates an equals problem. So if you remember for these, we're going to do the binomial PDF. So PDF is for the equals, CDF is for all the other inequalities. So we'll do 5.85 and 3. So whatever this is, the PDF just gives us the probability for that one value. So if I were to use the PDF up here, I'd have to do the PDF for like 0 and then the PDF for 1 and add them both together to get this same number that the CDF gives me all together here. Okay, so if I do the PDF for this one, I get 0.138. Okay, moving on, here we want the probability of 3 or more. So 3 or more is going to be greater than or equal to 3. So if you remember, greater than or equal to 3 is going to be this part here. So this is the part we want. And we're going to have to work with the complement to get that. Okay, because the CDF is only going to start at the value is only going to start at 0. So if we want it here to start at 3, then we've got to work around all that. And the way we work around it is to use the complement. So we're going to do 1 minus the binomial CDF, our N, and our P. And then on this, if we want greater than or equal to 3, then we need the complement to end here at 2. So that value is 0.165. Here we want to find the probability that more than 3 adults. So more than 3 would be greater than 3. Again, any of the greater than cases we have to use the complement on. So 1 minus. And this one, if we want greater than 3 is just 4 and 5. So the complement is going to drop down and pick up the 3 here. So the complement ends at 3. So our answer for that one would be 0.835. Okay, before we go any further, I want to make sure everybody is with me on the calculator. So if you go to second and VARs, it's going to bring up this menu here. There is other functions down below here. So if we scroll down, I have to scroll all the way down to A and B. Okay, here are the two that we're going to be working with. This, as soon as it stops moving. Okay, so here are the two that we're going to be using. So let's just try the binomial CDF to kind of show you what that's going to look like. So for me, it brings up trials. This is where you'd enter the N. The P is your probability of success, and here's your X. So let's say that our N, like on this problem, was 5.85 for our probability of success, and our X value was 3 in one of our problems. And so this is the probability that it gives me here. So it's definitely much easier than having to do the formula for each one of those. You'll just choose the binomial PDF or CDF as appropriate there. Okay, so here's a problem. This one, between 1974 and 2011, there were 460 NFL football games decided in overtime, and 252 of them were won by the team that won the overtime coin toss. So we're kind of checking to see, is there anything to winning the coin toss as far as the outcome of the game? Is the result of 252 wins in the 460 games equivalent to random chance, or is 252 wins significantly high? So in order to answer this, we want to find the probability of 252 wins or more in 460 games. So the probability that the number of wins is 252 or more. So greater than or equal to 252. The greater than type problems, we're going to have to use the complement. On this one, our N is 460. Because the wins and losses are equally likely, then we're going to use 0.5 here. And then as far as where it's going to stop, if this one's starting at 252, the complement has to end at 251. Before I go on any further, this equally likely part actually comes up a lot of times. If you have a gender problem, gender problems are always going to have a probability of 0.5 because we assume the likelihood of having a boy and a girl are about 0.5. So that's one thing I wanted to mention here with this. So moving on to answer this, put that in your calculator. And we're going to get 0.0224 for our answer. So as far as answering the part about is it significantly high, remember to compare it for significance purposes. We want to compare it to 0.05 and it's less than that. So it would be a significantly high number of wins just by chance. Okay. So it shows it's unlikely we would get 252 or more wins by chance. If we effectively rule out chance, we're left with the more reasonable explanation that the team winning the overtime toss has a better chance of winning the game. So basically, what that's saying is that if it's very unlikely that it happened by chance, so therefore there must be something to the theory that winning the toss affects the outcome of the game. Okay, here's one that I would like for you to try on your own. First of all, make sure that it meets the requirements of being a binomial probability distribution, that you've got the two outcomes, that you've got that it's independent and so forth, and then go through and try setting these up and then check your answers. Okay, on this one, based on a Harris poll, 60% of adults believe in the devil. Assume that we randomly select 5 adults and find the following. So if we look here, we're going to be talking about 5 out of all adults. So we would have a situation where we could treat as independent even if we didn't know it was independent to begin with. We also need to have 2 categories. So our 2 categories would either be that they believe in the devil or they don't believe in the devil, basically, would be the 2 categories there. So the first one is an exactly problem. So we do the PDF on this one. And you're going to have your N. This is the P that you should use, and this is your X you should use. One thing I would say is, like, especially on quizzes and tests, write out what you're putting in. And if it's one where I'm asking to see your work, then I can give some partial credit and so forth with that. Here's one at least 2. So at least 2 would be greater than or equal to 2. Any greater than problems are going to be done as 1 minus the binomial CDF. So that's going to be your N, your P. And in this case, if we're talking about greater than or equal to 2, the complement has to stop at 1. And so this is the answer that you should have gotten. Here's an at least 1 problem. So in the past, when we did at least 1, we would do, it's the same, we would do 1 minus the probability of none, which is the same thing as 1 minus the probability that all don't believe, okay? And so we would set it up like that in chapter 4. But now that we've moved on to talking about these binomial distributions, we can treat at least 1 as simply greater than or equal to 1, and then just do it like we've been doing here. So 1 minus the binomial CDF. If we want greater than or equal to 1, and this is actually should be a 0 here, and okay, so the correct answer, this is the correct answer, but do make sure that you make this correction here that this should be a 0, because the part we want starts at 1, which means it has to end at 0, and that's why I wrote down here this actually equivalent to saying 1 minus the PDF at 0, because 0 is the only one you're going to be adding the value for here. Okay, so just to kind of summarize that, if you're doing at least 1, at least the probability of at least 1 is 1 minus, sorry, my pen does not like to cooperate sometimes. Okay, so the probability of at least 1 is 1 minus the probability of none. That was kind of how we looked at it in chapter 4. And that will work, you know, whether it's binomial or not. But if you do have a binomial case with the 2 categories and you have an at least 1 problem, it is fine to go ahead and treat it as the x greater than or equal to 1. So that would kind of be the chapter 5 approach to this. Okay. And so this is just kind of showing you some of the tables here for this particular problem. If we were looking at least 2 and we didn't have the if we didn't have the way to use your calculator, then you have to literally find each one of these and add all of them up in order to get that. Okay, so the last concept, and I do have several examples still to look through, but the last concept is that of finding the mean and standard deviation when you're talking about binomial distributions. So in section 5.1, we spent a lot of time finding the mean and standard deviation for just a general probability distribution. It wasn't specifically binomial. So sometimes when it is binomial, then you're able to actually use these special formulas. So instead of having to set up the table and do the x times p of x and the x squared times p of x and add them all up and that whole process that we went through, you can simply use these small little simple formulas and get your answer, which is much nicer. Okay, and it also will allow us to be able to quickly find if something's significantly low or significantly high, or whether they're not significant at all. So if they're significantly low, then it's going to be less than or equal to the mean minus 2 standard deviations. If it's greater than or equal to the mean plus 2 standard deviations, then it's significantly high. And if it's between those, then we consider it not to be significant. Okay, so this is a going back to the football examples. In the previous example, our N was 460 overtime wins, and we had a P of 0.5 and a Q of 0.5 by assuming that that the likelihood was going to be the same. So what we want to do in part A is to find the mean and standard deviation for the number of wins. If we're specifically looking at groups of 460 games, so out of 460 games, how many wins would we expect with this? So our expected value or our mean is what's going to answer this. So if we look at the mean, that's going to be N times P. So our N is 460 and our P is 0.5. So we're going to get 230 for our mean. For our standard deviation, the standard deviation is the square root of N times P times Q. So that's going to be 460 times 0.5, and our Q is also 0.5. So that value is going to be 10.7, and we're going to round that to 1 decimal place. Okay, so this is our standard deviation, and this is our mean. So when it's binomial, which this one was, then we can use these formulas where the mean is N times P, standard deviation is the square root of N times P times Q. So use the range rule of thumb to find the value separating the number of wins that are significantly low or significantly high. So that's going to be this mean plus or minus 2 standard deviations. So 230 plus or minus 2 times 10.7. So if we do the plus case here, we get 251.4, and if we do the minus case, we get 208.6. So anything above 251.4 would be considered a significantly high number of wins that might have us thinking that there is something to this coin toss predicting the winner. The 208.6, anything less than that, would also cause us to rethink our original assumption that that it was equally likely that they would win regardless of who won the coin toss. So looking at part C, is the result of 252 overtime wins in 460 games significantly high? So 252 is slightly above this, so it would be considered to be significantly high, although just slightly. Okay, I have a few examples that I have pulled out to finish this section to give you lots more practice with how to do these binomial distributions. So what I'd like for you to do is to try these. I really, really encourage you to take the time to try these. That's why I'm giving 2 days on this lesson, is so that you can try them and understand what it is you need to be doing. So pause these and then advance the slide and check your answers. Okay, on this first one here, if you look at this, assume that when blood donors are randomly selected, 45% of them have blood that is group O. So we're going to let P equal 0.45, and that's going to be our O donors. Okay, so if there are 8 blood donors, so that's our N, find the probability that there are 3 with group O blood. So we want exactly 3, so this is going to be a PDF, and you can see your N, your P, and your X here to get this value for your answer. And the next one you want at least 5, so at least 5 is going to be greater than or equal to 5. So we're going to do, because it's greater than, we'll do 1 minus. It's a CDF, and here since 5 is included here, it's not going to be included here. We have to stop it at 4. The next one, no more than 3, is going to be less than or equal to 3. So the binomial CDF, you don't have to do 1 minus out here or anything like that. So we'll do the binomial CDF, and we're going to go all the way up to and include 3. Here, fewer than 5 will be less than 5. So no 1 minus out here because it's not a greater than problem. But we do need to stop at 1 short of getting all the way to 5. So we need to stop it at 4. Okay. Here, more than 2 would be strictly greater than 2, so we would do 1 minus for the problem. And since greater than 2 would be starting here at 3, then the complement itself is actually going to end at 2, and that's why this 2 is here. Okay, for the mean, it is binomial, so we can just go straight to our formulas here. So n times p, round these to 1 decimal place, and these are the answers that you should get. Remember, when you take your standard deviation, take the square root of the unrounded. So don't go over here to the 2 and take the square root. Take the square root of the 1.98. Okay, here's another one to practice with. Okay, so in this one, we're told that we're going to take blood samples from 25 randomly selected people. So our sample size is 25. It's a composite sample, so we want to find the probability of having at least 1 positive. So we're going to let this represent the number of positives. So this is going to have to be the probability of a positive. Okay, so these need to correspond here together. So this is saying we want to find the probability that we have 1 or more, or at least 1 positive. So we're going to do 1 minus the binomial CDF of our N and our P, and then this is going to be 0, because if we want greater than or equal to 1, the complement needs to stop at 0. When you put all that in, this is the probability that you get. Is less than 0.5, so it's not considered very likely. Only about a little more than 3% of the time are you going to have to go back and test a complete sample and look at the individual samples that made it up. Okay, here's another one to try. Okay, this one is talking about 800 subjects, so this is going to be my N. And they say the probability of a positive test is 0.28, so that's the P. Q is going to be 1 minus that, so 0.72. So it asks us to find the mean. So we're going to do 800 times 0.28 will give me the mean. The standard deviation is the square root of N times P times Q. So we'll do that and get 12.7. The minimum usual value is going to be the 224, which is the mean, minus 2 times the standard deviation. And then this one's going to be the mean plus 2 times the standard deviation. Okay, this is another one for you to try. I will say be very careful with your probabilities on this one. Okay, when I look at this one here, when someone buys a ticket for an airline flight, there is a 0.925 probability that the person will not show up. So the probability that they don't show, which is what I've written here, is 0.0925. An agent for Air America wants to book 32 persons on an airplane that can only seat 30. If 32 persons are booked, find the probability that not enough seats will be available. So basically, if you're booking this flight and you're booking 30 people on a plane that can only seat 30, the problem's going to occur when we have more than 30 people show up. So 30 people's fine, 31 people is a problem. So we are only concerned really about the probability that more than 30 people show up. So this is a number that shows up. So just keep that in mind. Right, so it's a greater than problem, so we'll do 1 minus, so we'll do the CDF. Our n is the total number, the 32, because your x is always got to be less than or equal to your n. So your n will be the larger of the numbers. Here, if we need the probability that they show up, because this number here has to be the probability for the ones that show up. So there is a way to set this up by doing the probability that they don't show up and kind of flipping it around. And so just because you did it a different way doesn't mean it's wrong. But if we're going with those that show up, then we need the probability that they show up, and that's 1 minus the probability that they don't show up. So that's where we're getting this number here. And so if we want greater than 30, we need the complement to end here at 30. Okay, so when I put all this in my calculator here, I get this as my answer. So about 19.1% of the time, the flight's going to be overbooked. So it would be a concern. I mean, almost 20% of the time, there would be a concern and have to be dealing with overbooking. I think this is one of the harder problems that you may have, just because you have to be careful about the probabilities matching up there. Okay, here's one. I really like this one. It's a good one on gender discrimination, so try this one. Okay, on this one, we're talking about a situation with a large firm here, and they've only hired 4 women among the last 34 new employees. So, is that coincidence? Is it chance, or are they discriminating? That's kind of what we're looking to do. Is decide that. So, basically, if they are equally qualified, then because they're equally qualified, the probability of selecting a man or a woman should be 0.5. So that's the probability that we would use. So it says help her address the charge of gender discrimination by finding the probability of getting 4 or fewer women when 34 people are hired. Okay, so if 34 people are hired, what's the probability of getting 4 or fewer? So x less than or equal to 4. So that's just going to be a binomial CDF. We don't have the 1 minus here. We'll use 0.5 for the probability, and we'll see that we get this as our answer. I wrote it like this so that you can see that we do have this out to the side, because 3.08 is never going to be a probability. If you see that, you need to keep looking because there's something else out here. So that tells me I need to move this 6 places to the left, which gives me this as my answer. And this is very, very small. It's very close to 0. So what that's telling me is if in fact everybody's equally qualified, males and females, and they're only hiring 4 out of 34, then that is very rare for that to happen just by chance. And therefore, they must be discriminating in hiring females. So if this number were a lot higher, then I wouldn't feel so much like it's discrimination. But because it's so low, it's very unlikely that they would only pick 4 females if it truly were by chance. And so therefore, they must be discriminating. Okay, here's another one to try. Okay, on this one is talking about acceptance of shipments. So if one shipment of aspirin tablets actually has a 3.5% rate of defects, what's the probability that the whole shipment will be accepted? And if you look up here, the whole batch is accepted if there's only 1 or none that doesn't meet the required specifications. Okay, so if the number of defective ones is less than or equal to 1, which would be 1 or none, then the shipment's going to be accepted. So here that would be a binomial CDF. We're looking at a group of 30, and they have a probability of being defective, which is 0.035. And then if this is 1, then this is going to need to be 1 here. So we end up with this as the probability. So the probability that there is either one or none out of a batch that's defective is 71.7%. So most of these batches are going to be accepted, but in saying that most will be accepted, there's still quite a few that are not going to be accepted. About 28, a little over 28% are not going to be accepted. So that is kind of a large number that's not being accepted. Okay, here's a problem for you to try. Okay, so on this one we have an 8% defect rate, so 0.08 is the probability of a defect. And we want to find the probability that among 65 phones, 2 or fewer are defective. So that would be less than or equal to 2. And this is the number of defects. So this needs to be the probability of a defect. Okay, so binomial CDF, we're looking at samples of size 65, a defect rate of 0.08, and then 2. So we get this as the probability that we would have 2 or fewer that are defective. Okay, 10,000 tickets are sold at $2 each for 3 prizes. What's the expected value of the gain if you purchase 1 ticket? Okay, looking at this one, if we set this up, you could either win $100, you could win 500, you could win 1,000, or you could lose. So you would set up your net gain or loss to indicate, how paying $2 for each ticket, what you would expect to gain or lose. So we would either gain $98, we would gain 498, we would gain 998, or we would lose $2. Probabilities of each of those, there's one $100 winning ticket, there's one $100 winning ticket, so the probability of that would be 1 out of 10,000. Same for the $500 ticket and the $1,000 ticket. And the probability that we're going to lose, there's going to be 9,997 losing tickets out of 10,000. So we know that we find the expected value by finding the mean. So we're going to do x times p of x. And I just kept these as fractions. You could convert them to decimals if you prefer. So we're going to add all these together. When we add them all together, we get this as our expected value. Okay, so to conclude today, I'd like to hop over to StatCrunch and just kind of show you how StatCrunch works. Okay, in StatCrunch, go ahead and go into StatCrunch as we've done before and go into My Groups, and that's going to take you to the data sets that we're going to be working with. But within StatCrunch, if you go to Stat, go to Calculators, and go to Binomial, it's going to bring up a binomial calculator. So what we're going to do with that is actually very easy, in fact, easier than the calculator to use. So let's say that we were wanting to do a probability where our sample size or our n was 25, and let's say our p is 0.85. Okay, so we'll change those. And then down here, we can actually choose which one we want to do. So if you remember, we went through the 5 different cases, and you have to choose like PDF for the equals, and you have to do the complement on the greater thans, and you have to adjust your ending value on the less thans, and we had a lot of different variations there. If you can just literally pick which one you want with this, and it gives you the answer. Just keep in mind that it may show this e negative 14 and you have to move your decimal. But let's say that we want a greater than. Okay, let's maybe greater than 3. Okay, so we can change it to that. And this is just plotting the distribution itself, but this is your answer over here. So in doing that, you don't have to do the 1 minus or any of those things that we talked about before. You can just simply change your values and you get your answers. So it's very convenient, very easy to use, but you still have to know how to set the problems up to use this. So I would like for you to know how to do your calculator and StatCrunch. because you may not have access to StatCrunch in another class, but it is a good software program to be familiar with.